two tables. First is characteristic table and excitation table. And I have given one hint for which we should write the characteristic table, and for which flip-flop we will write the excitation table. And then we will find out the Boolean expression, and accordingly we will design the flip-flop, the circuit. Okay. So today we'll take a few examples, and we will today only will see the conversion of flip-flops. Okay, so the procedure how to convert a flip-flop was okay. So the question can be written in two types: implement JK flip-flop using SR flip-flop. This can be the question, or they can write convert SR into JK. Oh, obviously these are flip-flop, SR flip-flop into JK flip-flop, correct? So what was the steps or procedure? First we will find out which one is available flip-flop or the required flip-flop. Anything you can write. So I'm writing what is the available flip-flop. Let me write the flip-flop which is required first, because we need to write characteristic table for that. So the required flip-flop, and for this case, which is the required flip-flop? JK. And obviously, if this is the required flip-flop, the remaining one is available flip-flop, and you will write the characteristic table for the required one. The second step is available flip-flop, that is SR flip-flop. The third step is write characteristic table for required one. So for this question, we will writing the characteristic table for which? JK flip-flop, correct? And the fourth step was write excitation table for the available one, and which is SR. And the last step was writing Boolean expression in terms of the previous state and the input of the required one. Yes, we'll see. Okay, so solve this question. So we have identified which one is required, that is JK flip-flop. So we'll write the characteristic table for the JK flip-flop. So do you remember how to write the characteristic table? Right. Okay, for writing characteristic table, what do you need? Previous one, correct, and the inputs. And we will writing this for the next stage. So there will be 8 combination for this three type of variable we have here. 0, 1 0 1 1 0 0 0 1 1 0 1 1. So I will write 0 1 1 1 and 1. And now we will write here the next state according to the previous one and the inputs. Correct. So if it was 0 and we have applied 0 and 0 at the JK flip flop. So if you remember the truth table, so it is a memory state. So it will remain in the previous state, that is 0. For 0 1, if you don't remember, I will give one hint here. Compare this JK as SR. Okay, so this is S means set and this is K is reset. So whenever K is high, it means it is reset, regardless the previous one. It should be reset. Reset means 0. For set and 0, J is high and K is 0, it means it will be 1. And this is toggle, Q and bar. How do you write for 1 1? So it will be 1, again 1, this is 0, and this is 1, and again it is 0. So we have completed the CR characteristic table for JK flip-flop. The next stage is writing excitation table for the available one. So what is the excitation table SR flip-flop? So by now, I assume that you remember this, how to write it. So for excitation table, you will writing this table for the excitation that are inputs. These are the excitation to flip-flop. And what will be the, on the left-hand side on the table, this will be the states, previous one and the next. Previous one and the next state. So there will be 4 combination. How do I remember this? I remember this 0 1 0 cross 0 1 0 cross. Check it. Otherwise, we need to verify this. Excitation table for SR flip-flop.
Yes, sir, correct.
Is it correct? Either we can verify, previously it was 0 and the next one is 0. So it may be 0 0 or 0 1. So R is don't care here, correct? And this is 1. So it has to be 1 because no memory. So 1 0. Yes, yes, it is correct. So you can also remember this for SR, how you fill. First of all, you need to make this correctly. This should be in this form. Yes, you will write 0. What is the weightage of these 2 digits? This is 0. What is the weightage of this 2? Is 1, 2, and then this is 3. So if you write in this way, you can write directly 0 1 0 cross 0. From now here 0 1 0 cross. And for JK, I will give one hint here. JK, it is 0 1 cross cross and 0 1 cross cross. But make sure your 4 combinations are correct. They are in order. Okay, so we have completed the SR flip-flop excitation for the SR flip-flop. Now what? Now the next stage is you will write S and R. These are the inputs of your available flip-flop. And how will you populate this table? According to this previous stage. And now the previous stage, you will compare this. This was the previous stage, and here this was the next stage. And if it was 0 and the next is 0 again, so what was the excitation table says? 0, don't care, isn't it? Now you will see here what was the previous one. Qn was 0 and again 0. So 0 0 similar, 0 and don't care. Now here 0 and 1. So 0 1, it was 0 and now Qn plus 1, that is next stage is 1. So I will write 1 in front of S and 0 in front of R. Now here for 0, 1 again, 1, 0. Correct. Now 1, 1 for 1, 1, it is cross 0. For 1, 0, 0, 1. 1, 1. Please correct me if I am doing any mistake here. And 1, 0, 0 and 1. Is it? Okay. Now we'll write the expression, that is Boolean expression. CAMAP, using CAMAP for S. So, and what will be the variables? So the variables will be J, K and Qn. So I have Qn here, and this will be J and K. So 0, 0, 0, 1, 1, 1 and 1, 0. Now fill this CAMAP. First is 0, then again, because these are three variables, Qn, J and K. And you're writing for S, 0, 1, 1, that is don't care, 0, don't care, 0. Is it correct? Okay. Now try to make possible largest group. So here I can make only this one. This will be your prime implicant. Correct. So how will you write expression for S? S will be what? Qn bar and J. Similarly, you will solve this for R. So for R, we have three variables, that is Qn, J and K. Have you obtained the expression, simplified expression for R? Don't care, 0, 0, then 0, 1, 0 and 1. Isn't it? Okay, so we can make this group, and it will be, R will be what? R will be Qn and K. Qn and K. So we obtained the expression for R and S. Now we'll design the circuit. And we have this SR flip-flop with us because the question says that design or implement JK flip-flop using SR flip-flop. So we have this, and we need to make this a bigger one. Okay, this is my S and R, and here you have Qn. Correct. So what your expression says, S should be Qn bar and J. So we need one AND gate here, AND gate, and S should be what? S should be J. I should write it down, and this will be Qn bar. This is your Qn bar. Okay, now what is R? R is what? Qn and K. So Qn, we have Qn from this point. This is your SR flip-flop. So this is the way you design or implement one flip-flop using another one. Remember always, because student, they confuse, because you want to design JK flip-flop and you are solving for S and R, isn't it? But this is the way, because here we will connect one AND gate, or yes, always it will require AND gate. And so input will be J, and another input of AND gate is the previous state. Is it easy? Okay. So the next question is, implement T flip-flop using SR flip-flop. T toggle flip-flop using SR flip-flop. This is the next question. Okay, so how will we go for this solution for this question? The first step is which one is required and which one is available. So I will directly write the characteristic table for the required one, which is what? T flip-flop, isn't it? Here, this is very easy, means question, the statement is very easy. Sometimes they write like convert SR into T. Okay, so this may be confusing, but this statement is very easy. So we will write the characteristic table for T flip-flop. Toggle flip-flop. Okay, now what? Characteristic table means what you need? Qn, previous one, and the input, and you will writing for next stage. Say it quickly. There will be 4 combinations. 0, 0, 0, 1, 1, 0, and 1, 1. So accordingly, you will write the Qn plus 1, that is in the next state of the flip-flop. If 0, 0, the previously it was 0 and we are giving 0 as the toggle flip-flop. So property of toggle is what? If it see 1 at the input, it just complement the previous state. Isn't it? Toggle. Whatever it was previously, if the input is 1, it will complement that. If it is 0, input of the T flip-flop is 0, this is in memory state. So what it will be? Either you can remember with this way, this Qn plus 1 for T flip-flop is the XOR operation between T and the previous one, that is Qn. XOR. Yes, it is XOR operation. So we have completed our characteristic table here. The next stage is what? Write excitation table. Excitation table for SR. So we have written there Okay, no need to repeat it. There is a way to remember this 0 1 0 cross 0 1 0 cross directly. So should I move to the third step, that is obtaining the Boolean expression? Because we have written that excitation table of SR, and the expression will write for S and R. Now say it was 0 previously, and the next is also 0. So this will be what? 0 cross. That is 0 don't care. Here 0 1 1 0. S will be 1 and R will be 0. We'll compare this one. This is Qn and Qn plus 1. Now Qn was 1 and Qn plus 1 is also 1. So this table says that the excitation for this combination will be cross and 0, and for 1 and 0, 0 1. Now write the expression for S and R in terms of this two, input and the previous state. So S Kmap for S, so there will be only 4 cells, that is Qn and T. That is 0 1 0. Isn't it? Are you following this? No. So what is the expression you obtained for S? Good. S will be Qn bar T. And what will be R? Yeah, this will be Qn bar, whatever it is, say it, Qnt. Is it correct? Other students, please verify. Yes, this is correct. So now it is very easy to design this T flip-flop using SR flip-flop. You have SR flip-flop, you have this output Qn, and this one is Qn bar. So I just need one AND gate here in front of S and in front of R. And what will be the output of this AND gate? Output should be Qn bar T. So T you want to design, that is your T flip-flop, and Qn bar will be the complement of the previous stage. And here you have this T and Qn. So this overall block will be your T flip-flop. I think now you can convert any flip-flop. Just follow the steps and remember the excitation table, because it is easy to remember the characteristic table, but excitation table sometimes you can make mistakes because there are don't cares. So now we'll solve another question. Take any one. So what can we take? Now we have used SR. Okay, so we will not use this. Now implement D flip-flop using T flip-flop. It will be very easy. Solve this. Don't look at the blackboard. What is the question? Implementation of what? D. Okay. Using T. Correct. Because this is very important topic, you may find one or two questions in your final examination. That's why I am practicing, I am making you practice here. So what is the required one? That is D flip-flop. So we will write the characteristic table for the D flip-flop. The question is convert T flip-flop T into D flip-flop. Or you can write design or implement D flip-flop using T flip-flop. So characteristic table for that is required one. Which one is required? D flip-flop. That is very easy. So you need the previous state and the input, and you will write this for the next one, next stage. You have 4 combinations. Okay. So D means what? Data. So whenever you apply 0, it will be 0. You will apply 1, it will be 1, it will be 0 and 1. Isn't it? Now we'll write the characteristic table, excitation table for T. So how will you write excitation table? You need you will write in terms of the inputs, that is T and the previous stage. So there are 4 stages or the 4 combination of the previous one and the next one. 1 1. So what will be the input at T if it was 0 and 0? So it will be 0. If the next stage has changed, it means we applied 1, again 1, it was 0. Okay, those who have studied the previous lectures very carefully, it is very easy. Okay, now what is the next task? We'll write T here and we'll populate this table in terms of the previous and the next stage. So see there and answer me. What was the 0 0 says? 0 1 1 and 0. And yet you did not answer me. What is the T? What is the expression for T? Boolean expression.
D plus Qn bar.
What is your answer? Repeat it.
Sir, D plus Qn.
I think that is wrong. What is D plus Qn? We'll check it. Is it correct or not? Okay, so we'll use these 2 variables because this is the input of the, because we have this information. So Qn 0 1 and T D 0 1. So this is 0 1 1 1 0. Is it correct? So this is, I think this answer is not correct. XOR operation between Q and Dn. So T will be D XOR Qn. So whoever the person said the answer, he was moving in the bike. That's why he's not giving the right answer. Okay, so how will you design this? It is very easy. You need one XOR gate. We have D flip-flop with us. Okay. So here we'll connect it. This is my Qn and this will be T. So you can make a big box and this will be your T flip-flop.
Sir, but we have to make D flip-flop. You have written it wrong.
What is the mistake? Acha. Okay. Now I will give few questions that will be your home assignment. Using SR, we have implemented J and what? T. JK and T. So we'll implement D. And the second one is using JK SR. And this will be the most difficult one. You should try this at your home. Okay. I will give one statement or conclusion for this second question tomorrow. Tomorrow or means the next class. Also, you can try JK to D. D. These questions are for your practice. Okay, so now we have 10 more minutes. Are you worried about your quiz? नहीं होगा. Okay, so now we'll jump to the counters. Okay, and that is also a sequential circuit. So still we have 10 minutes, so we can try that. The next topic in this unit is counter, designing of counter. What are the types of counter? So today we'll see the introductory part of the counters. What is counter? Counter, as name suggests, this is the sequential circuit first of all, and this combination or this circuit will be counting something, isn't it? So according to that, there are few classification of this counter. Okay, the first classification, there are two types of classification. First is based on the clock pulse. And the second classification will be based on the counting, states of counting. States of count. Okay. So the first classification is based on the clock pulse. So there are two types of counters based on the clock pulse. First is asynchronous counters. Or we can also call this ripple counter. The second is synchronous counter. Which one is correct? This one or this one? Spelling. I think H should be there. Okay. And yes, and what is the difference between these two counters, asynchronous counter or the ripple counter and synchronous counter? So you see, if the building block of counter will be the flip-flops. That's why we have studied the flip-flops. Okay. So let's suppose we are using two flip-flops. So in asynchronous counter, there will be this type of arrangement. The output of the first flip-flop, let's suppose this is my A first flip-flop and the B second flip-flop. So the output of the first flip-flop will be connected to the clock pulse of the second one in this arrangement. This is for asynchronous counter. If you have more number of flip-flops, so the output of the next one will be connected to the preceding. Correct. And what is the synchronous counter? The synchronous counter have the simultaneously they have connected the clock pulse simultaneously, means in this way. So here, if you can see, this is my clock pulse. So which one is fast? Now I applied this clock pulse. You need output at this stage. Here you are obtaining the output at this stage. So obviously synchronous counter will be fast, because this counter, the second one or the next one, will be only active after the output of the previous one. Okay, so the first answer in the question paper, they may ask, write down the differences between the synchronous counter and the asynchronous counter. The first one is the clock pulse, the method of applying the clock pulse in the flip-flops. Okay, so in asynchronous counter, the clock pulse will be applied from the previous output. Okay, in the synchronous counter, we have a simultaneous, we applied the clock pulse as simultaneously. We apply one clock pulse to all flip-flops simultaneously. Okay, and the second difference will be the asynchronous counter will be slow due to the clock pulse arrangement, and this one synchronous counter, that is synchronous counter, this will be fast. Okay, so this is the two types of counters based on the clock pulse. And based on the states of count, there are three types of counters. First is up counter. The second is down counter. The third is up and down. When I say up counter, it means this type of counter will count from the 0, 1, 2, 3 in this way. The down counter will count from the higher number of state to lower state, that is 9, 8, 7. It may be 4, 3, like this. This may start from 2, 3, but the counting will be in this order, ascending and descending orders. Okay, and the third one is up and down. So it may count 2, 6, 1, 0, 9, like this. Okay, we will see one example and then we will close this class for today. in the next lectures, we'll try to design, we'll give some states. Means you need to design a counter which will count from 0, 1, 2, and 3. This will be the question. Design an up counter. This will count these states 0, 1, 2, 3. Correct. So we'll solve this type of question from the next class. They may say design a down counter which will count from 5, 4, 3, and 2. And they will specify which type of flip-flop you should use. Okay. So today we will see, I have one arrangement here. We have this JK flip-flop, and we have applied a negative edge triggering. Do you remember what is this negative edge triggering? Do you or not? Okay, because this was the solution for the race around condition, isn't it? There was 3 solutions. First was you can choose the propagation delay higher than the total time that is on time of the clock pulse. The second solution was the master slave arrangement, and the third solution was the negative edge triggering. Okay, and here I have applied the clock pulse to the next JK flip-flop. This is my A and this is my B flip-flop from the output of the previous one. So the output of this one will be QB and output of this one will be QA. Okay. And now I will connect J equal to 1 and K equal to 1 for both JA, KA, JB, and KB. Here KB all are 1. So you can make such type of arrangement and you can give 1 or whatever you want to choose. But this is the way I have written. Okay, now we'll try to observe what are the states. We have applied one clock pulse. So this is my clock pulse. Here I have applied here this for the first flip-flop. Now previously QA and QB both were 0, 0. Okay, as I said that this is a negative edge triggered flip-flop, both are negative edge triggered flip-flop. It means they will transit their states when they see a pulse that is falling edge from high to low. That is, this is my negative edge. So it was 0, it will remain 0 till this. The moment the flip-flop, first flip-flop A will see a negative edge, it will change its stage according to the inputs. Now I have input as 1, 1. So what will be the 1, 1? Means what will be the output according to the 1, 1? Toggle. Previously if it was 0, so it will 1. And it will remain 1 till the next negative edge. So this way I can have the output at QA. Now what will be QB? QB, for QB, this QA is the clock pulse. For QB, QA is the clock pulse, isn't it? So it will see the negative edge in this QA pulse. So it will remain 0 till this point. The moment it see the negative edge, it will toggle and till the next negative edge. Okay, when I decide this, this is my clock pulse first, sorry, 0. You can 0 or you can take at 1 also. Now this is my 1, 2, and 3. Now I will observe the output of this arrangement. This is my QB and this is my QA. You now say, for this clock pulse, that is 0th clock pulse, What is QA and QB? This is 1 and 0. Isn't it? Did I make a mistake here? It should be like this: 0, 0, 0, 1, 1, 0, and 1, 1. This is 0, 0. Now we have 0, 1. Now 1, 0 and 1, 1. Yes, see this one. Now observe this: when this is my first clock pulse and it is 0, 0, QA and QB both are 0, 0. I will check at this point. This is 0, 0. Here what? QA is 1. This is my 0th clock pulse. This is first clock pulse, second, and the third one. So output of QA and QB will be 0, 0 for the 0th clock pulse. Then it will be 0 and 1. Isn't it? Then it will be 1, 0 and 1, 1. And now what are these? 0, 1, 2, 3. So this counter is counting 0, 1, 2, 3 for each and every clock pulse. Correct? What happened when it sees the next clock pulse? Where were we? We were here. So let me draw this. Okay. So this will be the next. We have here the third clock pulse. This one is third. The next one, this is the fourth clock pulse. So according to fourth clock pulse, whenever it see the negative edge, it will be 0 and it will become 1, and this will remain 0. So at this point both will be 0, 0. So the fourth state or the fourth clock pulse will again count 0 and 0. It means this arrangement is counting from 0 to 3 only. At the next clock pulse, that is fourth clock pulse, it will again, the output of QA and QB will be again 0 and 0. That is why this is counter. It will count from 0, 1, 2, 3, 0, 1, 2, 3, like this. Okay. So we'll see all these problems. We'll design few counters. We'll see in the next class. And today we use the JK flip-flop for designing this counter. We can choose another flip-flops for designing this type of counters. This is also very important topic for your question paper in the final exam and for the competitive exam also. Okay, so we'll stop here for today.